Bienvenue. Well, I guess it's in English. Sorry about that. Welcome to the third webinar organized by INTRIQ in collaboration with COPL, Optical, Numana on quantum photonics. I'll be the host for this event, so I'll briefly introduce myself in a moment. We are now waiting for others to join. I invite you to share thoughts using the chat line or the chat channels, and I'll be monitoring this channel while the presenter goes through his presentation. But for question, I'd rather have you use the Q&A or Q&R, question-réponse in French. So use the Q&A for registering the question, and at the end of the presentation, I'll go through the questions for you. In the meantime, I invite you obviously to keep your video and your speaker off, such that there's no feedbacks and conflicts, and we'll manage the bandwidth for all of us. Okay, so it's 3 minutes past the half hour. So again, welcome to the third webinar organized by INTRIQ in collaboration with COPL, Optical, Numana on quantum photonics. I'll be the host, as I mentioned, and my name is André Fougères. I'm Vice President, Innovation and Technology at the Institut National d'Optique, or we prefer INO. INO is a private, not-for-profit research and technology organization, as you probably know, dedicated to industrial solution based on photonics. INO is active in a wide range of industries, and it offers R&D services extending from the TRL1 or Technology Readiness Level 1 or problem definition up to TRL9, which is industrialization and production. INO has been dealing with quantum 1.0 activities since 1988, and I can safely say quantum 2.0 for a bit less than 10 years, supplying services to different players and companies. For those of you interested in the commercialization of quantum technology, well, take notice of INO, and also take notice of our newly established incubator called Quantino. That said, the first webinar presented in September focused on the Optical Society of America Industry Development Association quantum roadmap presentation. And the second webinar presented in October was on quantum sensor, and more specifically on quantum magnetometer that is under development by the startup company SB Quantum. And now this third webinar will be presented by Raphaël Dubé-Demers, and we'll discuss recent development in the integration of quantum function into optical chips. So we move from quantum sensors to quantum communication and quantum information domain. This is a field that Raphael surely knows quite well, since he is the co-founder of the startup Ehva, which provides R&D services and industrial test solution for integrated optical circuits. Mind you, those optical circuits might eventually find application in quantum sensing. Raphael is a physicist by training. He likes to juggle with quantum, relativity, and chaos concepts, actually. And he started in photonics at Laval University in 2014, from which institution he obtained both a master and a PhD degrees. During that time, he also served as a team leader on wafer testing at Siena and other things. So without further ado, Raphael, you have the floor.
So hi, everyone. Thanks a lot, André, for the presentation. I'm going to try to do my best. It's an honor for me to be here and be able to basically discuss my passion and what we do. I must say it has been hard to basically get which level I shall use, because quantum is quite complex and it can go quite deep. And at the same time, we have not much time and most likely very broad audience. So I'm going to try to do my best. And I'm also going to try to do my best in English. I've been requested to do it in English. So I said, yeah, I mean, it's a practice even for me. So So thank you very much. I'm going to share my screen. Hopefully it's going to work well. So if I hear nothing, I will assume everything is okay, and I will start.
Everything is okay.
Okay, good. Sorry, I was seeing like the chat and things. I'm not just used to it. So, okay. The topic is quantum photonics. Of course, it is very, very, very broad. So what I wanted to discuss today is how we can integrate basically quantum mechanics and into optical chips. We have many reasons to attempt this. My goal is to make them maybe obvious and basically justify what Ehva is doing and why we are related to quantum photonics and what is our eventual intention in this field. Unfortunately, it's a Zoom video, so it might be hard to chat. I'll be there at the end for everything. So the overview is quite simple. I wanted to start with the foundation of quantum mechanics because I realized when we discuss with people, we have some a priori thoughts and reflex basically in our mind when we attack this. So what I want to do here is basically extract what are the 4 keys I'm saying for quantum mechanics, how it has been translated into what we call quantum 1.0, and then what about the interpretation of quantum mechanics? Because you have the interpretation and you have the fundamental aspect that people are trying to convey into this framework. And then quantum 2.0, so basically what is it now? And most importantly, what we do with, how we use it in integrated optics more specifically. And then Ehva and our relationship with quantum 2.0. So that's the plan of today. Hopefully, at the end of the day, you will have at least a sense of what we see here. So on top, it's a Nature paper showcasing the architecture of a quantum processor. Of course, it is not something that is as mature as standard electronic is, but the obvious power of the technology is there. And if you look just below, it's a qubit converter chip. So basically, that one has been demonstrated. They are able to convert optical domain photons, like in the visible spectrum, for instance, into infrared and back and forth. So just to showcase how photonics could be used to interface any quantum application with the exterior world, for instance. So again, my intention here today is maybe to go beyond quantum information and quantum telecommunication, right? So here are the 4 keys. It's very obvious that these are basically the 4 physical observations that people are trying to encompass into quantum mechanics. And I think it is important to do the difference and understand them. So maybe it's too much. I'm sorry if everyone knows it. But you know, in quantum mechanics, things are the quantization basically is the key essence. So if you want to define a particles, a state, a quantity that you can observe directly or indirectly, as soon as you have very few particles, the idea is that they are not a continuum number of value that can be taken, but just few specific ones. So here what you see is basically what they call the eigenfunction, or just the wave function of a particle in a well. It's a very classical one. Quantization, you know, has been known already. It's part of what I call quantum 1.0. So a classic idea is the photoelectric effect, right? So basically, if the photons that are incoming into a target are not energetic enough, they will not succeed at liberating an electron, right? The observation we've made and so on can only be explained by quantization of the photons and of the energy level of the electrons. That's basically it. And people don't really realize, but if you look at things like night vision, almost everything we use to multiply the optical power and things like that are actually using quantization effect. And then you have uncertainty. So the idea of uncertainty is related actually to the third element of quantum mechanics. Is you cannot basically decide if a particle is there and at which speed it is going, right? So you have, from a very fundamental perspective, we are not talking about any interpretation or is it a wave or a particle, just the idea of we cannot basically observe the whole system and determine exactly all of the parameters of this system. That is actually very fundamental to quantum mechanics. And of course, how we will use it in photonics will be directly following these facts. So what you have here is a probability density function. So in a well again, so it's the same image as before, just the different energy level. What's directly interesting here is that you have dark spots, and these dark spots, they just mean that you are not likely to find a particle here. So for me personally, I always tend to understand that as probability of interaction. So for me, you will see, I don't want to go too deep into the duality and so on. So basically, if I position myself at the given spot, will I have chances to interact with the phenomenon or not, right? That's what uncertainty principle is telling me, basically. And then you have, and yeah, that gave rise to what we call wave packet. And initially, what I will discuss is the collapse of the wave function. That's basically how quantum mechanics has been imagined initially. Duality is the same idea here, roughly correlated to the uncertainty, is that if we have some vision of the system, we can say things are behaving as particles, right? So here is an example of things we were doing when I was doing my bachelor in physics. So Bremsstrahlung is basically the deceleration of an electron due to a field, and doing this, you change momentum. When you change momentum, you must emit, a vector particle like a photons, for instance. So that's what you have here. So the decent way to explain this is just almost probabilistic, right? So the whole effect could be observed and explained using the particle notion of the system. But at the same time, with the same particle, assuming it is an electron, you can observe it under the form of waves. And basically, when we look at the Maxwell frameworks and everything like that, it becomes obvious that we've always considered electromagnetic waves as waves, basically. But that could be true, right? That's what is fun with quantum mechanics, and that's what I love, is that you could go on one hand and say an electron is a particle and a wave, and a photon might also be a particle, right? We are able to define a momentum to the electron, to the photon. It can be measured. So why not? Maybe the mass is just at a Planck limit. I mean, and it's related to the interpretation I will discuss eventually. And then the last key to understanding quantum mechanics is the entanglement. So from a very high level, if we don't want to oversimplify the problem and so on, we can just say that if we consider particles or waves or quantities, when they are entangled, it is equivalent as saying that they are somehow correlated. So the first thing to understand is that we cannot say entanglement is a black or white phenomenon. It is not. It has a strength. And entanglement is also very key to understand with the concept of complementarity. So it means that you can potentially observe a correlation in between a figure of merit on two particles. So basically, you could say that they are entangled, but they might have other figure of merits as well, maybe in other orthogonal of some way, physical layout. And then they don't necessarily are entangled on this level, right? So basically, you can use one of the metric to determine the state of the particle, and that would, as people imagine, create the collapse of the wave function. But what's quite interesting here is that it's not exactly how it happens, and complementarity has a role to do there. So again, the concept of probability and correlation is really important. And then the last issue here is superposition. So the wave function as being described, and almost all of the equations like that could be added, right? So basically, a given state can be formulated as a superposition of states. So these are, to me, the four keys to quantum mechanics. And as you would see, hopefully that's my goal, you will see it is not that straightforward to basically understand all of the phenomenon and basically understand how could we go from there to a complete quantum computer or things like that. So it's an example I'm going to take throughout the discussion. It's very easy to understand. It's based on the quantum key distribution. So if you have a look on the left, you have Alice, who is trying to transmit something to Bob. And then you have Bob who is watching, right? So the idea is always the same. You have one person that will transmit, you know, a quanta, a unit of a particle, and it will have some states. So one person can decide of its basis state, right? And it can be totally random. The sole idea is that Alice has to know when she is using a given basis, for instance. And then Bob can observe, you know, the results through his own basis. Eventually, they will communicate together. They will be able to assert if they have seen the same thing. And then they can basically discover, for instance, if the communication has been tampered with or not. That's just a very high-level example to showcase how we can use photons. But then it says nothing about entanglement and everything. So that's what we will see afterwards. So in Quantum 1.0, what happened is that people basically laid out the foundation of quantum mechanics, and they said, okay, these are a bunch of new phenomena. We will use them to build stuff, right? So here it was my question actually, but I think we can just move on. The question was, do you know devices which are Quantum 1.0 devices? And actually, usually the answer is, I don't know. But in fact, plenty of things that you know are using these initial effect, or at least could be explained by quantum mechanics. So like lasers, amplifiers, and things like that is just full of quantum justification. Most of the semiconductors and transistors effect of today are based on the fact that we are leveraging basically some quantum phenomenon. And then we could think of magnetic resonance imaging and many sort of imaging in general, energy generation, and a lot of diagnostic technique in the medical application. So basically, the idea here is just to understand, at least it's my vision, that Quantum 1.0 devices are not explicitly, for instance, using entanglement or one of the four keys of quantum mechanics. They are just explained through a quantum model of the underlying physics, but usually they will still be what we could call macroscopic system that have that exist in the classical limit, right? And then we have the interpretation of quantum mechanics. Here it is a subject that is really appealing to me because it helps not only, you know, have fun with the subject, but also understand and criticize the approach that people will use and understand the justification, because I think it is already safe to say you can always find someone that will disagree on your quantum perspective, and maybe you are both right. So I thought it was worth a few minutes on discussing the interpretation, because I'm not personally a big fan of the first interpretation, which was the Copenhagen interpretation. So the idea for them back in the time was that everything is classical, right? And when you do an experiment, you observe quantization and things like that. So for them, quantum phenomenon were an experiment. It was required to be an experiment. And what went out of this is the idea of a wave to represent particles. So then the wave packets. What is funny there is that the evolution of a wave function is 100% deterministic, but the description provided by this wave function is itself probabilistic. So we are saying we don't know the state of a particle, but how this is going to interact with another unknown system is deterministic. It is not all of the formalism that will say that. And here in this very interpretation, the wave particle duality is basically answered through a simple wave function collapse. So basically they say the particle is existing in a non-collapsed state, basically the wave function. And as soon as you will try to interfere with it, measure it, it's going to collapse into one state, and that is what you will measure. So the foundation of this theory has been made by Niels Bohr, which is also the inventor of the atom model and so on. But, you know, a lot of scientists, they were in strong disagreement with how it could be explained. So a lot of people were having a strong intuition or feeling or intention, at least, to believe in local realism. So the idea here is that the two particles, they might not be that much in an undefined state. It might just be us that is not able to discover this state. So one of the way people were defining local realism was through the introduction of hidden variables, physical quantities of some sort that you cannot feel, that you cannot access, but still are there and live within each particles, so that at each true instant, everything is always determined, just not accessible to us. But that gave rise to the Einstein-Podolsky-Rosen paradox, and gave rise basically to the famous Bell's inequality, right? Which are basically trying to give a boundary on this locality, right? So a lot of experiments have been done. Initially, they decided, the scientific community, that local realism and hidden variables were wrong. But nowadays, we found a lot of what we call loopholes, because at the end, it's always a matter of what is time and what is reality, right? So it's very interesting. And then that evolved, right? So people proposed what is known as, I guess, the first example of the hidden variable theory. And today it's known as the pilot wave theory. So basically, in this framework, it's the opposite way around. You have not really a wave function of a particle. A particle is a particle. It is just living on a... Yep. Sorry, I got comments. So yeah, anyway, pilot waves are useful for providing a lot of experience. I mean, sorry, I got the... So the idea of pilot waves is that basically the universe is a wave and the particles are particles. It is explaining much more decently a lot of features, but a lot of it is also hard to experiment, most likely, mainly the two-slit experiment. So if you read on that, you will find that this was maybe not the key solution. So people went with what they call the multiverse theory, and here it's just an iteration after what I would think is local realism and pilot waves. So here we can say that the wave function, they never collapse. They always exist. It's just that our universe is actually one big quantum state in a big multiverse that is made of all superposition of all possible states. But here again, the philosophical implication is somewhat not ideal. So then people went with relational quantum mechanics that basically says that states are observer dependent. So basically, you can never have a true system. Like in relativity, you never have a true or absolute time. You have geodesic and referential. So it's going to be the same in quantum mechanics. And basically, this new framework is able to explain a lot of things. Unfortunately, I think we will miss time. If you want to read very good books and very good discussion on philosophical aspect of the quantum mechanics, Carlos Rovelli is one of the guys to go for. It's really nice. And yeah, it's all linked to Gödel incompleteness theorem. So that's the philosophical question that I will not have time to discuss. So, okay, back to interpretation. I'm going to give you an example, and that's the introductory point for photonics and quantum. So what you have here in light blue is a waveguide, basically, and you have just a circular waveguide close to it. That's what we call a ring resonator. So the idea is that light goes in at some wavelength, it's going to enter in resonance, and then other wavelength will pass through. So if you observe the transmission spectrum, so basically if you shine light on the left and look what is going to be on the right, you will observe a transmission peak like that, where for each peak, basically, it means that at this very wavelength, you have a strong resonance, right? But when you start to think about quantum mechanics, you have fancy questions like, if I have just one photon, and this photon is going in the bus waveguide and is at a resonance wavelength, what will happen to him? How will he interact? And if we have a resonance, with what this resonance is happening, right? So then again, we could have very decent explanation using the pilot wave theory. So basically, the photon would perturb his environment such that he is creating a resonance into its surrounding environment. Or if we apply Lorentz transformation, for instance, we will say, well, this photons, you know, he sees the dimension of the ring as a 0 because the dilatation of time for him is infinite, right? That these are naive perspective, but I guess it's just a way to show how intriguing and how non-trivial this could be. And that's also explaining maybe how I can explain some of the things I do differently explained than other people. So if we go on what would be the quantum 2.0, for me at least, it means that these are devices which are making explicit usage of quantum properties such as entanglement or wave-particle duality or uncertainty principle or something like that. So a lot of implications are there. If you think about quantum 2.0, I would say measurements are now done at the quanta level. So it's not a quantum system that you explain, but that you look at it from a very classical perspective. You really live and measure at the quanta level. So therefore, all systems become probabilistic. And therefore, again, not a single measurement can be done and expect to yield basically the answer, which is totally different from what we would expect. And these are the challenges associated with that. Since we are at the quanta level, we are close to the physical limit. Generating and detecting a single photon, for instance, is not trivial. The system is probabilistic, but it is never isolated. So it is a big noisy system, actually, that you will try to build and measure. And since a single measurement cannot give anything, you need repetition. So it is also a fundamental aspect. And this is why I think silicon photonics in general has a true power to become the main platform for quantum manipulation and technologies in general, just because of how we can integrate these functions and basically overcome issues like repetition. So if we go again with the initial bit, well, quantum key distribution and the chip, the question here is, and the funny part is, how can we build that, right? So what people would do is that they would use what they call a ring resonator. On the left, they will inject a very strong signal. This very strong signal will create nonlinear effect and will create two photons, right? That are correlated, or we could even maybe say entangled, right? So if they have polarization relation, it is not a zero correlation. So then we have a filter and we just throw away the pump. And then we have another filter and we separate the reference and the signal, basically, that is to be transmitted. So here, what I'm trying to present is just a general way of thinking about quantum implementation on silicon, and that's the main idea here. So it goes a little bit beyond this, this presentation. So all in all, you can think that you have one system like that will generate these photons, or you can have on a chip tens of them, hundreds of them, thousands of them. That's the idea, right? So these basically will become photons generator. Of course, it is probabilistic, so you never know when a photon is generated. And if you need a bunch of them at the same time, the likelihood that they all happen at the same time is also close to zero, right? So you need a way to do that. So what people do in photonics is that they have a detection circuit that you see on top, basically, that will detect what we call the idler photons. And then the circuit will decide. It will know, basically, I have a photon there. So if I have one there, I must have the other one, the signal or the proto-qubit somewhere close to, at the same phase, basically, in the circuit. So again, the same game is going on. You have multiple decision circuit. So on one line, you decide basically if you have photons or not. And on the other line, you still have the photons or the wave packet, and it is still unperturbed. You have done nothing to it. If you detect, then the complementarity is also important here. If you detect the idler and you've done no attempt at measuring its polarization state, the proto-qubit will have the same freedom in its state, right? In this example, at least. So basically, people, what they will do is that they will try to generate a lot of photons. They will have decision circuits and delay line and so on, so that at the end, they can build this big multiple in, multiple out circuit, with at the aim is going to give a controlled flow of photons, right? That's the foundation of quantum computing in general in optics, I think. So what you have here is a result of a very, very interesting paper. That was what I wanted to talk about initially, but that might have been not a good idea. Here, basically what you have to understand is multiple photons and multiple entanglement and complementary condition that could be implemented. So here what you see is you have lattice or plane in the cubes. So one plane is a given instant, and in it you can use different complementarity protocols basically, and an entanglement feature to shape basically relation. So all in all, what you are trying to do here is draft the possible outcomes, and that's basically how you do a quantum computation. So without going into details, that's that. And more modern framework like this one are using also time entanglement. So you can entangle plane of photons with different metrics, and then you can entangle different planes of photons. So if you look at businesses like PsiQuantum, that is exactly what they are trying to do, which is, to me, a scalable architecture. And on the chip, it just looks like a bunch of interferometers all together. If you have the way you do the junction, basically will determine if you collapse or not some functions or properties, and that's basically it. So all in all, it is not too complex. And here would amount to the part where what I call the action is happening. So here it would be a quantum computation, for instance, that would happen here. That would be the purpose of laying out these photons and this specific entanglement scheme. And then you have a result. So at the end, you have a matrix of photons that had an interaction. You go again in the big MIMO, which is basically the decision or the end circuit. Again, here is just an example. If we were working with polarization, how could we retrieve it? Well, we would just put two photodetectors just after a polarization splitter. So here, we would basically understand if we had one or the other polarization state. And if we have a bunch of them and we know the deterministic actions that we've undertaken during the travel and the assembly and the interaction of all of the photons, we would basically have a result, which is the end of the computation. So with silicon photonics, what I want to transmit is it is incredibly scalable and reconfigurable. And maybe I shall have say quantum 3.0, but nonetheless, the idea is here. The level of power that you have in silicon photonics is immense, just because of mainly the repetition and the noise in the system. So you need a lot of redundancy if you want to have a given metric, right? So if you want to have a 100 qubit computer, you cannot have 100 generator and you cannot have 100 measurement. You need much more than that to accomplish this. But nevertheless, I'm going to jump in at Ehva and what we do. And it's all centered around this. For me, Quantum 2.0 at least amounts to finding a way to generate qubits, which are a bunch of particles where you can control their generation such that you end up with these nice little cubes that you saw, right? Because that's the paramount of the organization you can think of in a quantum system. And then you want to perform an action. So what I've described here was a computation of some sort. Quantum key distribution is just an idea, right? And at the end of the day, no matter what happened to these photons, right, you would like to measure them, basically collapse all of the states, realize what is the current measurement, and then you would like to decide basically what is the results. Do I need another measurement? Do I need to change? Things like that. So at Ehva, basically, I'm going to try to explain in a few minutes two things. First and foremost, what we deliver is a test solution for integrated optics. So as of today, that's like a silicon wafer that you see. It is not straightforward to test. And here is like the machine we built. It's generic and it is completely turnkey. So we aim to provide the first kind of generic machine to do that. As of now, people that work in the field, especially in telecommunication, they have to be really creative to get to a working station. But the station is kind of nothing if you do not have the automation solution that goes with it. So basically, the automation solution for us is much beyond just automating the lab, because automating the lab, you have frameworks to do that. You can easily generate navigation pattern from a wafer. You know, it's none really scientific. Where it gets really interesting is in the value proposition that we have for the people. Is that, yes, it is a test solution. You test basically what you need very soon at the cheapest cost. That's what we do. But then, since you have the machine and you have the whole solution, what you realize you've been doing is you've been acquiring a lot of data. And actually, the complete set of data needed to understand your process or your product. So basically, with Ehva, people can have not only just a test solution and then build their own connection to their business intelligence and data solution. It's already made, and people can accomplish things like reducing the test flux, engineer the yield of a given product. We were discussing about quantum mechanics. For us, the business case is quite straightforward and is related to what I said, right? It's close to the physical limit. So the yield, or how many chips are good, is very, very low. But since the power of the technology is very, very high, it is still a viable technology. Nonetheless, you know, you need to test, because 99% of what you will produce will not be good for the quantum application, but just this 1% makes it viable still. And yeah. So, and all in all, why it is even more important in quantum mechanics and what we are up to is exactly that. So from a very physical perspective, in our world, when you try to build all these nice circuits, you realize that you will have a wafer, and this wafer will have issues with it. Like the silicon will not be equally thick everywhere. The width of a pattern will not necessarily be exactly this width, and things like that. So you have different metrics that will change differently and more or less correlatedly, you know, in the wafer. So that's what you see here. But then as you've seen in the quantum circuit, you need many components all together. And if you want to have a complete working chip, all of the components, of course, they need to work, and they need to work well within specification. So what we are trying to do with Ehva here is really through the data solution and through IP block that we put on the wafer of people, extract basically the variation of these physical parameters like metrology style, and build predictive modeling out of the box from the components. So now people can decide that a given component, the best one is not necessarily the one where it's Gaussian curve, the center of it is the maximum, right? Is also the one that is correlating in its dependency with the other, right? So at least, for instance, if you look at the yellow one, if it is really thick over there, and all of my devices are really good when the silicon is maybe okay or too thick, well, I know I will have a big bunch of my wafer that will be good. But if just next to my device that is thickness sensitive, I have a device that is width sensitive, and I have these green and yellow pattern, basically the overall yield will go down quite fast, actually exponentially fast, as I will try to include new components. So the purpose of what we do is just to help people basically scale and build more complex stuff. And the other key thing here is that although it is even a bigger need in quantum, most of the metrology structure we do and most of the conclusion and predictive modeling we do are non-mutually exclusive, right? So we can work with a coupler or a tap and assume it as classical representation. You know, when you measure a power, basically it's a number of photons that you measure, again, due to the quantization. So classical measurement for me in optics is just a likelihood of what would happen to a single particle. So what we want to do eventually with that, and that's my last slide, I promise. The idea here is that we build this test and data solution for our customer, but it is also a very good vehicle for us to develop our own IP. So again, the idea is not to steal, you know, our customers or things like that. It's really to partner with them, because I might be interested in a component. I know many people that are interested in this component. It is not core component for all of us. It is just a pain. We need this coupler or special photodetector or things like that. So why not develop it together? Well, our whole data framework has been made for that. And we are licensing our own technology. So here, that's the last thing we would like to do if we have success. We are looking for partners to push this technology. The idea here is that we can basically measure and emit, so it's reciprocal, a photon with a known or unknown, basically, polarization. That's the purpose of this device, to measure the polarization. So basically, if you think back about the example of Alice and Bob here, these two devices could be used to replicate, you know, in free space, for instance, this experiment. Each one of them could dynamically basically build his own basis. Bob could have its random basis, and then as soon as they correlate this, it shall make sense. But the last thing here, and why I shall have said even maybe quantum 3.0, is what's the future of things like that? Because it's an interface with the world, and silicon photonics is like printing paper. It is hard to have this nice drawing, but once you have it, if you want millions of chips, you will have them, right? So it is a fantastic field. And at Ehva, what we aim to do here is push this technology first in the classical domain to build LiDARs, for instance, and material scanning devices. But of course, the same devices coupled with a high repetition generator, for instance, would make for a fantastic quantum LiDAR or things like that. And then we can imagine that this polarization effect is now sampling a protein, right? And we have an array of detector, things like that. And we are tomorrow, basically. So thank you very much. I hope it was okay. I hope I've not spent too much time explaining things you already knew, or I've not been too confounding. So I'm quite open for questions and hear back from you.
Well, thank you, Raphael. Excellent presentation. There's a first question from Sophie La Rochelle. Is the test solution limited to SOI?
Bonjour, Sophie. Very good question. Our intention is that no. So how we've built the system is it's basically a work canvas. It is not providing you with constraints. So in this sense, the station and the automation solution, what they allow you to do is define physical metrics that you want to observe, you know, test sequences and so on. And then the station is just a physical means to address the chip. So silicon on insulator is one, but we could have, you know, laser bar. We could test a lot of things, right? Once you have the alignment algorithm, once you have the navigation algorithm and the numerical vision to see the chips and address them where you would like to address them, we can. So yes, in principle, the idea here is that the station we have even at COPL shall be used for any or almost any integrated optics.
Thank you, Raphael. Are there any other questions from the audience? If not at the moment, I have one myself. Ehva is offering test solutions to the community, so I guess a lot of attendees are interested in what you have to offer. But then again, you're also developing your own devices with your own IP. So in that sense, you might need some help from others. So what's your main hurdle pushing forward your company and making it a success? Do you need help from anyone? And if so, on which level would that be?
Thank you for the question. It's a nice question. I think, the test solution wise, it's going well, and we are doing basically the proof that we can sell these systems and that they are of value. So that, of course, instead of using our solution or purchasing stuff from us, I think we are good. Two things that we would need is from the data solution. I haven't said it, but it is working with an AI module, right? So how could you reduce the test flux by understanding all of the metrology measurement? You have the deterministic way to do it. You have a probabilistic way to do it, and then you have a meta-analysis that could be done on the form of an AI modeling, all right? So people that have data and that would like to, even if you keep them for you, we are looking for proof of concept for that kind of claim. We would be quite interested in implementing solution on some project, or just consuming the data and stressing our data environment. That's basically it. And the other thing we would like is the polarimeter that I've shown you, and ring resonator and so on. I truly believe that these are key devices. Of course, we do not have the manpower, the bandwidth, anything, right, to really say we will build a product out of it. Of course, the roadmap is tens of millions of dollars. So anyone that feel they have a synergy in some components like that, we would be quite happy to partner. So we already partner with people for the development, for instance, of ring resonator and modulator. The key here is that we all reserve a field of use in terms of IP. So everyone is happy, everyone joined forces, and at the end of the day, everyone will get a way home with what he needs, right, to his own entity. So that we need. Synergy, and even what you do at INO, here is just a big open shout to everyone.
All right, thank you. Any other questions from the audience? Going once, twice. Oh, there's a question from Claudine Allen. In the many optical quantum computing schemes being developed, do you see some emerging that do not require photon number resolving detectors?
You mean like single photon detectors?
Photon number resolving detectors, meaning a detector that will tell you how many photons it acquired during the measurement time. It's not a counter. It's really if it's hit by 20 photons, it needs to say 20 photons.
Oh yeah, well, I mean, I guess that's the big drawback of the using silicon photonics is yes, you need a very cold environment to detect these photons. I am not aware of a big breakthrough there. Okay.
There's another question from Alain Villeneuve. What is needed for logical qubit? Also, what is the difference between qubits and no-roll qubits? I don't know what no-roll qubit means.
Yeah, I don't either.
Maybe Alain wants to jump in and ask his question directly. Alain, we can't hear you if you're trying to address the crowd. Well, anyway, Raphael, can you answer the first part of the question? What is needed for logical qubit?
Well, I mean, basically the question I think is what is a qubit, and for me, it's just a particle or a wave that will have again that will exhibit quantum phenomenon such as an undefined state. That's basically the only thing you need. So if you do not think about entanglement and things like that, and you just go with the picture I've shown you of the quantum key distribution, the qubit is just basically a photon that is traveling. As simple as that. Of course, you can shape them and understand them in a much more complicated ways. I'm not sure if that helps.
Well, I think from the correction I've seen being posted, he's
I
asking
haven't
also
seen.
about the difference between a logical qubit and a normal or physical qubit. That's what I get from his second part of the question. So what is the difference between a logical qubit and a physical qubit?
Oh, error-corrected qubits. Yes, I mean, okay, so if you go more deeper in the quantum processor architectures, you need to do a measurement. And what I said is that it's noisy. So to me, a corrected qubit happens once you've basically removed or decorrelated anything that you could have done on this qubit. But again, I would not say it's a black or white system. It's like noise and measuring the error rate in telecommunication. You improve the situation, but do you have a true error-corrected qubit? And then the same goes for what would be the quantum memory and how would we preserve it? I think a lot of open questions are still there. I don't know if that was the.
Yeah, I think it's okay. Waiting for maybe another question. Alain is actually thanking you for the answer.
Okay. Oh, now I see it. Okay, sorry. It's easier like that.
All right, so it's quite close to the end. So any other question? Once? Any other question twice? And if not, well, let me thank you, Raphael, again, and a good, really interesting presentation. Good luck for the company. I hope that you can help the community, and that I hope that the community can help you as well. So thank you again, and thank you for Numana, Optonic, and COPL for organizing this webinar. And well, have a nice day all. Bye-bye.
Thank you very much. Merci beaucoup.